Welcome to Unit 8, Inference for Categorical Data, chi-squared. This is video over topic 8.5, setting up a chi-squared test for homogeneity or independence. Alright, so these 4 steps for setting up a chi-squared test are going to be very familiar. In fact, we've been using them for quite some time now. Number 1, name the test and give the hypotheses. Number 2, check the conditions for the test. Number 3, find the chi-squared values and the p-value, and then make a conclusion. These are the same 4 basic framework that we've been working with anytime you run a test for significance. Now, in this video, we're going to focus on a test for homogeneity and a test for independence. All right, so what test is it? We do have these 2 different types of tests, homogeneity and independence. Keep in mind, anytime there are counts of data across one categorical variable being measured, is always a goodness of fit test. I don't care how many categories you have. If there's only one variable, but there's 20 categories, well, it is still a goodness of fit test. However, when there's 2 categorical variables being measured, again with multiple categories, then it's either going to be a test for homogeneity or a test for independence. Now, when you're working with 2 categorical variables, they will always have a two-way table showing how those 2 categorical variables interact with each other. So the real difference lies in how the question is asked and presented. That's what's going to make the determination between a homogeneity test and an independence test. But the procedure for both tests that you're going to learn in this video are exactly the same. Let's first talk about a test for homogeneity. A test for homogeneity is when a categorical variable is explored across multiple populations. A homogeneity test explores the claim that there is a difference in the distribution of that categorical variable across populations. So let's just say we're looking at a categorical variable of brands of vehicles. You got Ford, Chevy, Volvo, Audi, Lexus. The list is, I don't want to say endless, but there's, sitting here for a while and probably list vehicle manufacturers. So that's in of itself, that would be a goodness of fit test. But if I introduce another categorical variable, and that would be the distribution of those types of vehicles across Germany, Russia, Spain, United States, Canada, maybe 5 different countries. So now I'm looking at 5 different populations, these 5 different countries, and the distribution of those car types across those different populations. And what we're looking for is there a difference in those distributions of car manufacturers across those populations? And the null would be that there is no difference. So, for example, if 10% of people in the United States have a Ford, well, then 10% of people in Canada have a Ford, 10% of people in Germany have a Ford, 10% of people in Russia have a Ford. That would be when they're meaning that we're talking about it being the same. And then the alternative is that there is a difference. So the question will focus on asking about the distribution of a particular categorical variable across more than one population. You will clearly see 2 or more samples taken from those 2 or more populations. All right, when you do have a hypothesis for homogeneity, they're actually quite simple, and you're going to type these out. These are going to be written words. These aren't symbols here at all, okay? So here are the appropriate hypotheses. So the null is that there is no difference in the distribution of a categorical variable across populations. So again, this would be saying that, if 10% is Ford, it would be the same for every single one of those countries. If 15% were Chevy, it would be the same percentage for all those countries. If 1% were Lexus, it would be 1% for all those countries. That's what we would be talking about with the null here. Now, I also have in parentheses here, or treatments of an experiment. So maybe we're doing an experiment where we have a block design where we have Americans, we run an experiment on them. Then we have a group of Canadians, we run an experiment on them. We have a group of Germans, we run an experiment on them. So it'd be the kind of this exact same thing. So the null would be that there's no difference in the effect of the experiment on each of those populations. And the alternative would be that there is a difference in the distribution of a categorical variable across the populations. And, maybe Ford is 10% across the board, but if Chevy's not, well, then I'm sorry, you don't have the same distributions across. And they don't have to be the same number or the same proportion. It's just got to be the same for that category. So like I said, maybe Ford is 10%, Chevy's 15%, Volvo's 3%, Lexus is 1%. So the numbers aren't going to necessarily be the same, but the proportions are. And so the alternative would be that, at least one of them is different. That's all it really takes, is for one of them to be majorly different to throw it all off. Now, You don't have to dive too much into detail when you're writing these hypotheses. You're just talking about the generic distribution of that variable. So I'd say, hey, there is no difference in the distribution of car manufacturers across the different countries. And then the alternative would be there is a difference in the distribution of car manufacturers across those countries. In a specific problem, and that's what I was kind of just alluding to, in a specific problem, make sure you really add that context of what those categorical variables are. All right, let's now turn our attention to a test for independence. A test for independence is when we are asking if there is an association between the two categorical variables, which means not independent. Remember, if there is an association between two variables, that means they are not independent. So an association means that one variable's outcome affects the other. So for example, if I'm a man, then I'm more likely to do this, versus if a woman might be less likely, or so forth. Who knows? So an association, meaning that one variable impacts another, or the presence of one variable makes the other more likely or less likely. For example, if it is known that being a boy makes you more likely to have blue eyes, then there is an association because being a boy changed the likelihood of me having blue eyes. So that's what we mean when we say there is an association. So if a question specifically gives you a two-way table and it says, hey, is there an association between the two variables in this table? You're clearly talking about a test for independence. Okay? Now let's talk about the hypotheses here as well for a test of independence. So the null would be that there is no association. Absolutely not. Being a guy doesn't make you any more likely to have blue eyes than a girl. 20% of people have blue eyes, 20% of guys have blue eyes, 20% of girls have blue eyes. There is no association between eye color and gender. Whereas the alternative hypothesis would be that there is an association between the two categorical variables. And remember what I kind of mentioned earlier is maybe blue eyes, you see 20% across the board, 20% blue eyes for boys, 20% for girls, but all of a sudden brown is majorly different. Maybe like 30% of boys have brown eyes, but only 2% of girls have brown eyes. If you see, it doesn't, I guess the point I'm trying to make is that if one category is way off, then you might go with the alternative. So you don't have to be specific in the alternative or the null about one category in itself. You're just being general, talking about the two categorical variables. So eye color versus gender, right? And if one of them is off, then you're going to find that out in this chi-square test. And then if that's true, you would go with the alternative hypothesis. Excuse me. As mentioned before, though, in a specific problem, always make sure you're writing these null and alternative hypotheses with context. Okay, let's run through the conditions. We've already seen these conditions before, if you remember back from the chi-squared goodness of fit test. But number one is that samples must be randomly selected to avoid bias. The size of the samples must be less than 10% of the populations to assume independence. And I put the S in parentheses there because if it's a test for homogeneity, there's again going to be multiple samples from the multiple populations. So again, all of those samples must be random and all of those samples must be under 10% of the populations they were taken from. And then the third condition, as we mentioned before, is that there must be 5 or more expected counts in each category. Please keep in mind that it's the expecteds that have to be 5 or more. You might have an observed count be less than 5, and that's okay as long as what was expected for that category was 5 or more. All right, so let's take a look at a problem here to get things rolling. So this is an example that we kind of alluded to a little bit earlier in previous videos, but we'll finish it off here. So 3 different random samples were taken, one from middle school students, one from high school students, and one from college students. And students were asked to name their preferred social media app. The results are in the table below. So we see a nice two-way table here with one variable on the left, and that's your age, I guess, middle school, high school, college. And then across the top, we see the other categorical variable of what is your preferred social media app, Facebook, Instagram, or Twitter. And we see all of these values. So again, on the outside, the totals, those are called our marginal values. These are just our totals. And then on the inside, those are our conditional values, right? For example, that 12 is very, very specific. That is 12 middle schoolers who prefer Facebook and so forth. So those are the numbers that we're really looking at. Those are the observed values that matter really most to us, are these values right in here. The totals are needed, and you'll see that when we talk about getting the expected values, but it's really those inside numbers that are the observed values that we're looking for. So the question here is, does the data show significant evidence that the proportion of favored social media app is different across the 3 populations? conducted tests at the 1% level. So we want to see, is there a difference? That's what we're asking about. Is there evidence of a difference between the proportion of social media apps? So let's just jump right into the hypotheses, because hopefully this should make sense. Now, this is a chi-squared test for homogeneity. Notice that we are looking at 3 different populations, and we are asking about, is the distribution across those populations different? Those are all signs that this points to a homogeneity test. So the null is, of course, there is no difference in the distribution of social media preference across the 3 populations of middle school students, high school students, and college students. Notice the context thrown in there. And again, remember, the null is what we have to assume to be true, that there is absolutely no difference. And what that means is if 10% of people use Instagram, well, then 10% of college students do, 10% of middle school students do, 10% of high school students do. It would be the same percentage across the board. And then maybe Facebook is 30%. Who knows? Whatever. But that's what we mean. Again, you don't have to name numbers here at all, but that's what we're alluding to when we say that there's no difference in that distribution. And the alternative is that, whoa, there is a difference in the distribution of social media preference across the 3 populations of middle school, high school, and college students. So notice how similar these 2 sentences are. The only difference is that the null says there is no difference, where the alternative says there is. And again, remember, we're always looking for evidence of a difference. That's the alternative. Now, step 2 is, of course, checking those conditions and finding the expected values. So for each sample, we select was selected randomly to avoid bias. Each sample is assumed to be less than 10% of the population for which it was drawn. I assume that 150 middle schoolers is less than 10% of all middle schoolers. I mean, even if we're looking at one particular school district here, one particular city maybe, these numbers should all be under 10% of the population, unless it's some real small town, obviously. And then again, we have to get the expecteds first before we can actually officially check that 3rd condition. So part of step 2 is getting those expected counts. So in the previous video for 8.4, we learned about how easy it is to get the expected counts. You just take the row total times the column total. And again, the order there doesn't really matter because you're multiplying, and then divided by the grand total. So where did I get 21.05 expected Facebook users for middle schoolers? I took 150 times 80, so the row total times the column total divided by the grand total of 570. And you literally just repeat that for every single one of those values in the middle of the table. So that does take quite a bit of time. So if you want to pause and kind of check my work on here, I believe I checked it twice, but I do make mistakes sometimes. I round to 2 decimals. You don't ever want to go to a whole number. These are expected counts. These aren't necessarily things that are true. They're expected. So please make sure that you keep at least 2 decimals. Now, just so you understand here, where these numbers are coming from, it's really important that you understand that I build this assuming the null is true. So, for example, 80 out of 570, right? 80 out of 570 is about 14% of people in this survey who use Facebook. So if there is no difference in the distribution across the populations, I should see 14% of middle schoolers. So that'd be 150 times 14%. Yep, right about 21. I should see 14% of the 200 high schoolers. Yep, right around 28. And I should see 14% of the 220 college students. Yep, right around 30.8 that use Facebook. Again, they don't have to be the same numbers. A lot of kids think that I need to see 21, 21, 21, the same exact numbers. No, it's the same proportion. That's why you have to start with that total, which is again about 14%, and then work across. And then repeat for Instagram and Twitter. So remember, it's really simple when you can, there's one thing between doing it and understanding it. I hope you understand it and know how to do it, but some kids at the end of the day, they just remember row total times column total divided by grand total. All right, so that's it for this video. We are going to do one more problem, but when I say that's it, we're only going to explore steps 1 and steps 2. In 8.6, we're going to explore actually finishing it off with the chi-squared values, the p-values, and the conclusion. So that's what this video is for. This video is just for setting up the test, going through step 1 and step 2. So let's move on to another problem that is a test of independence. So here, a random sample of 620 registered voters from a large county in California. So notice that this is one sample of 620 people from a large county in California. They were asked what was their political party affiliation, and we noted their gender as well. So we got gender on the left, political party across the top. And again, these are our marginal values, our totals, and then the numbers on the inside are really the most important ones that we're going to examine. So, does this data show an association between gender and political party affiliation? The fact that you see that word association instantly tells you working with a test of independence. They want us to conduct this test at the 5% level to find out. So again, the null would be that there is no association, and then the alternative is what we're looking for, and that there is an association. So let's walk through those real quick. So the null is that there is no association between gender and political party. So if I'm a guy, I'm just as likely to be Republican as a girl. No association whatsoever. And the alternative, which I forgot that should be an H sub A. Sorry about that, little typo. There is an association between gender and political party for registered voters in the county of California. Now, again, you don't have to specifically mention male, female, independent, Republican. You're just giving the overall categorical variables, gender and political party. Because maybe you find out that for one political party, there is no association, but if for one of them there is, then I'm sorry, there is an association between the two variables. So that's the null and that's the alternative. Pretty simple. Now for step 2, check those conditions. Of course, they got to be random to avoid bias. 622 voters. Let's assume less than 10% of the population. It did say it was a large county in California. So again, adding that word large county tells me that, I don't know how many people are in that county in terms of the population, but I'm pretty confident 622 is under 10%. And then that there are 5 or more expected counts in each category, which of course you got to get the expected counts before you can officially check that condition off. So once again, here is the totals I got. These are all the expected values. So again, for example, let's talk about males that are Republican. So I took the row total, 340, times the column total, 173, and I divided by the grand total of 620. And you literally repeat that process for all 6 of these values. Notice how I kept 2 decimals as well. So let's just talk about, again, I really want you to make sure where these numbers come from. So for example, 173 out of 620 is about 28%. So about 28% of people in this survey were Republican. If there was no association of the 340 males, I should see 28% be Republican. And that would be about 94.87, right around that number, right around 94.87. And then again, same thing of the females. Again, right? If about 28% of people are Republican, then 28% of the females are Republican. That would be no association. You would see the same percentage across the board. So 280 times about 28%, yep, is right around 78. So that's exactly where we're getting those numbers from. And it really makes a lot of sense, whether at the end of the day you just remember row total times column total divided by grand total, or you actually understand how these numbers are calculated and what they mean in terms of there being no association, because those expected values are always calculated based on the null being true. All right, that's it for this video. I just wanted to go through those 2 examples, one being homogeneity, one being independence, and then we will continue on with these examples in the next video for 8.6, but we'll actually finish it off, how to do step 3, get the chi-squared values, find the p-value, and then with that p-value, of course, we make our conclusion, as we've been doing for what seems like months now, right? So, all right, guys, that's it. Best of luck. Hopefully this all made sense to you.